Hi, today we'll see hardware software co-verification and synthesis in brief from module 5. Hardware software co-verification. From the name itself we can tell that it is a part of verification which includes both hardware and software. In an embedded system, much of the system functionality may be implemented in software that interacts with hardware. That means both software and hardware together we are going to study now. In order to verify functionality of the system, need to verify the software and its interaction with the hardware. If it is a combined one or embedded one like that, we cannot go for checking out only the hardware or the software. We have to verify both hardware and software. If we had hardware models of the processor and the instruction and data memories, could verify the software by simulating its execution on the hardware model. We have to go for simulating it, then only we can tell that it is working. Load the instructions into the instruction memory and start the simulation. The operation of the processor, fetching and executing instructions, and reading and writing I/O controller and accelerator register would then be simulated. That means each and every components which you are having in the hardware has to be simulated using a software. The problem with this approach is very slow, since simulation of each processor instruction involves simulation of much of detail of hardware operation. So this will make the system to get verified or simulated very slowly. Fortunately, there are approaches we can make or we can take to make the hardware software co-verification much faster. First approach is to recognize that software and hardware development are usually done by different people, allowing the software development team to start software verification as early in the design process as possible to reduce the overall time to complete the system. So what is the first step is you have to go for allowing the software team to start the verification at the earliest stage itself rather than waiting till the end of the process. Next is the lower layer, sometimes called as hardware abstraction layer on the board support package for processors that are component on PCB contains driver code and interrupt service routines for I/O controllers, memory management code, and so on. It provides an abstract interface that can be called as application layer. With this division of the embedded software development and verification of the application layer code can proceed without waiting for the hardware design. So depending on the requirement, we have to go for choosing that whether we have to go for verifying the hardware or software. Instead, a software verification tool can emulate the operations provided by the hardware abstraction layer. For more detailed verification of embedded software, we can use Instruction Set Simulator ISS. What is the use of that? Means rather than compiling and executing the software on the host computer, the ISS use code compiled into the instructions of the target embedded processor. So instead of going for checking individually in one by one system, ISS will be more useful. It then simulates execution of those instructions but without simulating the detailed hardware operations of the target processor. So this saves you time as well as effort will be less because ISS is providing a good functionality over there. Simulation of software on an ISS is intermediate in speed between native execution on a host computer and execution on a hardware model of the target processor. So we can analyze what is the use. If you are going for an ISS, it is very helpful for you. So this tool can perform analysis as well as debugging of the software. The platform support layer can be emulated, allowing verification before the hardware design is available. So what we can do in this sense, stage by stage, we'll go for software verification. This verification can be done and no need to wait for until the hardware design is available. If your software is ready, means then we can go for checking for the hardware design. Once the hardware design team has developed models of the hardware that interacts with the embedded software, can perform co-simulation of hardware and software. That's what I was telling. It is no need of waiting until the hardware component has to arrive. We can finish off the software and later once the hardware comes, means we can go for co-simulation. This usually involves collaboration between an ISS and a simulator for the hardware model. Two simulators run concurrently, communicating when the processor performs bus read and write operations. I just want to show you the overall design flow. You can see functional design already we have gone through. All these things which you have gone through is coming under functional design only. Now we have to go for synthesis. Once you finish the synthesis, it has to go for place and routing and then system integration. Finally, we'll go for fabricate, and once fabrication is over, we'll get the end product. Go for synthesis now. Having performed functional design and verification of a digital system, the next stage in the design flow is synthesis. That is the refinement of the functional design to a gate level netlist. For most designs, synthesis can be performed largely automatically using an RTL synthesis tool. Where a design is complex, has very high performance requirements and is implemented as an ASIC, it may be necessary to custom design the circuitry of some subsystems. Automatic RTL synthesis particularly used for FPGA based designs. RTL synthesis, as the name suggests, it starts with models of the design refined to the register transfer level. A synthesis tool starts by analyzing the model, checking to make sure the code conforms to its style requirements. It also performs some DRC, which is nothing but design rule check, such as checking for unconnected outputs, undriven inputs, and multiple drivers on non-resolved signal. All those things will be checked using or when you are going for analyzing the synthesis method. The tool then infers hardware constructs for the model. This involves things like analyzing what all things we will identify when you are going for synthesis process only. We are going to tell now. It will analyze wire and variable declaration to determine the encoding and the number of bits required to represent the data. We'll check all those things. Then analyzing expressions and assignments to identify combinational circuit elements such as adders, multiplexers, etc. and to identify the input, output, etc. and intermediate signal connections. We will check all those points when you are going for synthesis. Also analyzing blocks to identify the clock and control signals and to select the appropriate kind of flip-flops and registers which has to be used. For ASIC, technology library is usually provided as part of a larger design kit by the ASIC vendor, that is the company that will ultimately manufacture the ASIC design. So ASIC, the technology library itself, they will give for synthesis. We can go for synthesizing it using from the kit what they are provided by the ASIC vendors. For FPGA, the technology library is usually embedded in the tools provided by the FPGA vendor. So we can analyze that if you are going for FPGA or ASIC, whatever it may be, the technology library is there in the there given by the vendor. So we can use it easily. Typical components in a technology library including the inverters and non-inverting gates with a small number of inputs, small multiplexers as well as chain components and flip-flops. So if you are going for a typical components, if you are verifying a typical components in a library, we can see all these components. The process of translating the design into a circuit of library components is guided by synthesis constraints that specify. Such constraints include bounds on clock periods and propagation delays. While relying on the synthesis tool, it determines what all it will do in the sense when you are going for synthesis tool, what all it will do in the sense, it determines the implementation for much of the design. There are cases where need to directly instantiate specific predetermined implementation. So it will check the implementation, how it is taken care. One such case is use of components created using the core generator. We have already gone through core generator. It creates both a simulation model and an implementation optimized for target implementation fabric. It is a generator which is going for taking part of both hardware and the software. While synthesizing the design, instantiate the version of the generated code that includes the optimized implementation. Synthesis of a design is followed by a further verification step, in this case to verify that the implementation produced by the synthesis tool meets timing constraints. Simulate the implemented design to ensure that it meets functional requirements. So we have to go for checking that when you are going for synthesis, we have to make sure that the functional requirements are being met. Functional requirements have been met. Otherwise, it is difficult for you to go for the end product. However, there are two good reasons for performing gate level simulation. First is the technology library includes estimates of timing parameters of the components used in gate level design. The gate level design allows to verify that the design still meets functional requirements taking into account these timing parameters. It may expose subtle timing errors that were not evident in the RTL code. Second one is there are ways in which we can write RTL model code that produce different behavior in the RTL simulation and the synthesized hardware. A synthesis tool should issue a warning in some cases. What will happen is in some cases it will go for issuing the warning that this is not proper, that is not proper. But thing is, if you are going for complicated design, it is not necessary for you to go for taking care of all those things. So what will happen is small issues they will go for neglecting it. Simulating the synthesized design and making sure it behaves the same way as the RTL design is a good check that we have used